the current process of how we assess the risk that Bangladesh faces from tropical cyclones is first we have climate models that describe land, atmosphere, and sea conditions of the global climate. They can be models of our future climate or current climate models. And from these climate models, we do a process called tropical cyclone downscaling, which takes the coarse wind distributions of the climate models and is able to produce synthetic specific cyclone tracks. So we can produce thousands of synthetic cyclone tracks through tropical cyclone downscaling. The reason this is important is because history has not produced enough cyclones for us to do a proper analysis and risk assessment on. So we must synthetically produce cyclone tracks. And after we have these cyclone tracks, we can run a physically based simulation to simulate the storm surges that result on the coast of Bangladesh, and from there we can assess the risk of different regions of the coast. However, one big issue with the current process is that the hydrodynamic simulation, so the physics simulation of water levels, is computationally very expensive and requires a lot of computation of solving physics equations. So to give an example, let's say we have 5 different climate scenarios. These might be current climate or future climate that we want to risk assess on, and different organizations produce slightly different models for different climate scenarios. So there's 10 climate models per scenario, and we don't know how much the sea level will rise in the future, so it could rise some amount of centimeters or more than that or less than that. So let's say we have 5 different sea level rise conditions. To do an accurate risk assessment, we probably need around 10,000 cyclone tracks, and we might want to see how sensitive this assessment is to change. So changing one of the cyclone tracks by a little bit, how much that affects the storm surge. And Bangladesh is not the only site that suffers from tropical cyclone risk around the world. So let's say there's 1,000 of these sites. Doing all of these simulations, we would require around 280 gigawatt hours of power, which is enough for an electric vehicle to drive to the moon 4,000 times. And we definitely want to save on computation. So the solution that I worked on over the summer is I'm continuing to work on this as well right now, is making a machine learning model that takes thousands of input cyclone tracks, and from this input, it can figure out which tracks have high potential for destruction. And for the ones with high potential for destruction, we run the hydrodynamic simulation on those tracks. And for the rest of the tracks, there are cyclones that will pass through Bangladesh and not cause an extensive amount of destruction, so we do not need to run the simulations to assess risk for the low destruction potential cyclones. So doing that, I ran 3 different experiments. So the first experiment is... So how does these experiments work is that I train the machine learning model on some amount of tropical cyclones and then test it on other tropical cyclones. And if the tropical cyclone track creates a storm surge level greater than 3 meters at some point along the shore of Bangladesh, then that cyclone will be classified as greater than T, or greater than the 3-meter threshold. So for the first confusion matrix, so these are confusion matrices, which plot actual over predicted cyclones being either greater than the threshold or less. So the first one on the left, the machine learning model was trained on 75% of ERA5 data, and ERA5 is just a present climate model that has benefited from observations of the present climate. And that trained on 75% of ERA5 data and tested on 25%. And we can see that the accuracy is pretty good, and only 9% of storms were misclassified. So for the middle picture, it was trained on all of the ERA5 climate data and tested on SSP5 8.5. And this model is just a future climate. It's a model of the future climate that assumes economy growth fueled by fossil fuels. So we can see that we can train the machine learning model on present climate scenario storms and accurately produce predictions for the future. And then the last picture on the right is showing that machine learning does not need a lot of data to be skillful. So this machine learning model was trained on only 20% of the ERA5 data and tested on the rest of the ERA5 data. And its accuracy is only slightly less than that trained on much more of the data. So we don't need to produce a lot of synthetic cyclones to produce like a machine learning model that will accurately predict which cyclones are destructive. So it shows that there's a potential for modifying the current workflow of risk assessment for tropical cyclones by adding in this machine learning model that pre-filters out the most destructive cyclones before running the storm surge simulation.